Picture on there.
Oh, yeah. No.
Can we eliminate that thing at the top?
Well, that, we just having that conversation.
Oh, sorry.
This is yours. I could move directly.
It'll show back up if somebody goes in. I know.
Don't worry about this. I can let them in, so you don't need to click on that.
Okay. All right, let me see. All right.
For the people include the exploratioCd, I don't have to carry them on with me to Finland. For the Finland expert people, I know there are quite a few of them here. You can select the charge from you.
Oh, yeah. Do I use? You know, these are my.
Yes.
Just stand
There
there.
is,
I can.
there is certain passing the microphone.
Yeah, I can.
Yeah, I think those are on.
Okay. I'm not gonna move around.
I'm gonna sit right in front of you. Do you want me to pass you?
Sure. All right.
We just put the timer on 15 minutes. So do you want, how much time do you want for the first one?
I'm gonna be taking it out. I mean, not now. I finish it like. Sometimes I go.
For the first one?
Yeah, and then the second one, I mean. There's no. Just flash it to me. This one. And then the second one. You can flash it.
Hey. Shall we start? Okay, thank you very much for joining us for this geophysics session. I know it's a bit unusual with all the other talks we have here, but I really appreciate everyone being here. We're going to have a slight change of plans because one of the speakers has been unable to attend because he's currently 3 kilometers underground. So that makes it a little difficult to get here, but you know, things do happen. He may walk in the door. So I will be taking part of Musamanzi's time. I'm going to give a very short summary of some of the exciting things he's doing and why he's 3 kilometers underground. And Carol will take the rest of his time. So we will just expand that. Also, Janine Cole, for a variety of health reasons, has been unable to attend, and Carol will be presenting her talk. So we will carry on from there, and welcome to Carol Finn from the USGS of Denver, Colorado. And she and I have been collaborators for a while. And yeah, it's a long story. Okay, so thank you. Over to you, Carol.
Thanks, Sue, and thanks everyone for the invitation to do the keynote. So I'm going to talk about geophysical imaging of selected layer mafic intrusions, focusing mostly on the Stillwater, the Duluth, and the Bushveld, but with some reference to some other intrusions. It's not comprehensive or representative in any way. And then talk a little bit about how you can relate these to issues associated with platinum group exploration, as well as understanding the genesis of deposits. Well, I don't really need to say too much. I think everyone in the room knows this better than I do, that layered mafic intrusions are the sources of the PGEs in the world. Slide shows some of the exploration, geophysical exploration for PGE deposits. Most of the time we can't detect them directly. Things like the JM Reef, for example, in the Stillwater complex, despite it's the highest grade PG layer, doesn't really show up because of any of the, for example, electrically conductive minerals are disseminated. And so most of the time we're using the geophysics to characterize the environments in which these deposits occur. So I'm going to give some examples. The first one that we often look for is layering, and various data sets can detect layers. And I'm going to show you how we use the MAG data in the Stillwater complex to detect layers. So this is a map of the Stillwater complex in Montana, geologic map. Was in place 2710 million years ago into a metamorphosed sedimentary, mostly sedimentary basin with some plutons. It was uplifted in the Archean and then cut again in the Cretaceous during the Rocky Mountain uplift. So it's been quite dissected. And I'll talk about that a little bit later. This map shows flight lines of a airborne magnetic and electromagnetic survey flown over the complex about 20 years ago. So there's a lot of filtering we can do with magnetic data to isolate anomalies of interest. And one of the things we can do, which you may have seen, are edge detection methods. So basically we can detect magnetic contacts, which can be many things. They can be compositional, they can be faulting. And in this case, I did a bunch of filtering and then isolated the places where I thought the contacts were, which are all of these black lines. And the first thing we can see is this pink line where there's quite a lot of contacts lined up along this. This is the JM roof. So it does detect it. This colored, these colors here indicate a very high resolution geologic map. And a lot of these black squiggly lines follow these layers. So when you take known geology and put the magnetic contacts on it, you can identify what they are. And these letters refer to letters over here in the stratigraphic column for the Stillwater complex, ultramafic to mafic rocks. And why you're seeing them in the magnetic data is over here. These are all olivines. And where the olivines are serpentinized, secondary magnetite is formed. And so therefore it's why it shows up in these maps. So this is just an example of where you can take all these squiggly lines that are confusing, tie them to something you know, and start to look for either, in this case, mineralization, but at least know where you are in the section. And you can apply this to places that are not as explored as the Stillwater. So from the electromagnetic data, we inverted the data to get resistivities and also susceptibilities. And these are slices from 15 meters into this model. These purple colors are highly resistive areas. It's kind of what layered mafic intrusions look like. They're generally not very magnetic. In the susceptibilities, you see these little lines, those are dikes. So those are important to know where they are because they can interrupt mineralization. What we're interested in are these blue colors because sulfides can lower electrical resistivity, and sometimes the sulfides are in the ultramafic rocks, and if they're serpentinized, they show up as magnetic anomalies. Usually ultramafic rocks, not always, are not usually very magnetic. So I'm going to show you a couple of profiles across the models. Here they are. This is the resistivity profile, and here's a susceptibility profile. The EM data only saw about 80 meters depth. It's what's called frequency domain. So it's got high resolution, but not a lot of depth penetration. And these methods like to find low resistivities areas and the very low signal in resistive areas. So sometimes it's hard to penetrate. We picked this profile for a couple to show the core, how you can match. This is soil geochemistry. So this is log of copper in percent, log of palladium in percent, to show how we can then use the geophysics together with soil geochemistry to come up with some ideas about mineralization. The JM reef is in pink, as it always is in these pictures, and the picket pin, which is another mineralized horizon, is in blue. So if we go here, this is a mineralized area. You see low resistivities and low susceptibilities. Iron formation is very magnetic, but also can be low resistivity. And sometimes there's sulfides in these iron formations. So it's important to know this. So this is a good example where you can see mineralization. The JM reef, in this case, is in a little resistor, and these conductive layers water also lowers resistivity. I'm going to talk about that a little bit more on the next slide. Picket pin, you don't really see it. So this is kind of what I was saying, is that you don't often see some of the reefs and things that are important. The mag data shows the location of dikes, which, as I said, can interrupt mineralization. So this next slide, another geologic map. This is the LiDAR, beautiful. You can see in the LiDAR data, some of the layering in the Stillwater. This green line here shows the outline of a very large landslide. And our profile crosses it. And here again is the JM reef. And it's right here in this cross section. It sits right near where this landslide is. the top surface in the model's resistive, which is what you expect. I mean, that's where you see usually the resistive complex, but you see this layer here, this lower resistivity. And I was very surprised to see this. I see this, I work on volcanoes and I work on volcanic landslides, so we see this in a lot of places. What I think this is water, and the reason you can see it is there's a rubbly layer at the bottom of this region, because this is a big landslide. And so you wouldn't want to drill here. So this is another sort of application of this kind of data of helping actually locate drilling and where you might want to avoid. And there's other landslides that you see the same kind of thing. Mike Zintek, I've been working with Mike for a long time. A lot of you know him. He's an economic geologist. And it's actually a key part of this whole Stillwater project, where Mike and I worked together for a long time. And so anything I know about economic geology, I know from him. And he's able to really use the geophysical data in a way that works for him intuitively and do it right. Because as a geophysicist, sometimes you see geologists think, oh, I can just interpret this data. And the interpretations are not robust geophysically. And I know all of you think the same thing about geophysicists interpreting geologic data. But Mike took the models of the resistivity and the susceptibility and put them into an unsupervised classification and came up with these categories. So like very high resistivities and low susceptibilities, for example, are typical of the complex. But I'm going to focus on these two areas, and we're interested in these colors, the blue colors. We've got the lowest susceptibility and the lowest resistivities. And there are boreholes here showing where there's copper nickel mineralization and outline where the sulfide targets are in green. And you can see in this area, we actually have a few of these blue blobs indicating that we see these regions with the geophysical data. And if you go to the southeast, where there's also quite a lot of boreholes, you can see even a more extensive area that might be targets for mineralization. These are small, but that's what the targets often look like. And some of them are deep. So we have deep sensing geophysics that show that there are probably sulfides at depth. All of these other colors that are similar are shales, and we know where they are because they're mapped. But the other important thing about them is they're all fault bounded. They're Cambrian, younger shales, and you want to, but knowing where they are tells you where there's faults, even when they're not mapped, which is also important for exploration. So the second thing I'm going to talk about is when can you see evidence for sulfur oxide saturation? You know better than I do the importance of sulfur in making PGE deposits. I'm definitely not going to go there. This is a picture. This is from the Bushveld. This is a geologic map of the Bushveld complex. I'm focusing on the northern lobe here. This is a gravity map. And there's a magnetotelluric line right across here indicated by these stations. And also, like the airborne EM, it makes resistivity maps, color scales reversed. They like red because they often use it for volcanic areas, so it's hot. And sulfides lower the resistivity of rocks, graphites do. And what we see here this is all transvol right here. So there's sulfides here at the surface. So we have ground truth that sulfides are producing these low resistivities. Shales do as well. And so what you see here is the white line indicates an inversion for the Bushveld, which I'll talk about. But all of this shows that the transvol is here, and we know it has sulfides in it because they're mapped at the surface. And this was a little bit of a surprise because the transvol is only exposed here and then a little scrap here. So the northern lobe looks like it's coming into the Archean rocks, but in reality, most of it's in the Transvaal Basin. Most of the rest of this talk, I'm going to focus on this, which is this part of the exploration criteria, which is really looking at the extent, the thicknesses, the volumes of these intrusions, and also the crust contains them. And there's a lot of different geophysical methods that we use to do this. I'm going to start with the Duluth complex. This is work done by my colleague Dana Peterson. Picture the Duluth complex and Lake Superior. This is in Minnesota. This is the study area, and the Duluth complex is part of the Mid-Continent Rift System, which is a failed rift. It's full of lava flows and this layered mafic intrusion that intruded a sedimentary basin, very similar to the Bushveld with the Transvaal. Here, the gray shows the sediments at 1095 million years old. Here's the Duluth complex. It also intruded older volcanics that are shown in green, and there are diabases here that are contemporaneous with the Duluth complex. Here's the gravity map. These red colors indicate gravity highs, and the blue colors are relatively low. This is the magnetic data. I'm not going to talk about this too much, but these are the inputs to our modeling. So this process that I'm going to describe here is one that we also use for the Stillwater complex that I'll show you later, and the Bushveld. So what we do to start is we start from things we know. We know the topography. In this case, there's depth to glacial sediments above the Duluth complex. Dana put that in here. This layer is just basically taking the bottom of this glacial layer and adding about 10 kilometers just to try to get a starting model for how thick the Duluth complex might be. And then we know from seismic data that there's high velocities in the lower crust, which would translate to high densities that I will talk about in the second talk extensively about the importance of including these in these models. Very poorly constrained, however. And then we apply densities that are based on rock properties to these models. And our approach is typically to say, apply all these density, fixed densities in a layer and let the inversion, the program, invert for thickness. How thick does the layer have to be to match the observed gravity anomalies? This is the result. I'll show it in a more easy to see picture. But then we also let it go and listen until we feel like the thicknesses are reasonable, and then allow the densities to change in the modeling. And this is these are Dana's results. This is the thickness. So the blue colors are lower thickness. So it's averaging out here about 5 to 7 kilometers thick, except in these couple regions, which are under these late diabase intrusions. These are very thick. So probably feeders to at least the diabases and probably part of the Duluth complex. This is what kind of densities that come out of the modeling. We fix the ranges. We don't just let it pick anything, and it's all reasonable values for what we have sampled at the surface. So that's the Duluth complex. Let's move to the Bushveld. This is a map showing the extent of the layered mafic part of the Bushveld, the Rustenburg layered sweep, not including the granites. It's big, as everybody knows. I mean, this area is basically the size of Ireland and Wales together. For Americans, it's the size of Maine. And it's exposed in various limbs. It also goes into Botswana as the Molopo Farms complex. It was intruded 20, 50 million years ago, mostly into the Transvaal Basin. Here's the gravity map where you see gravity highs, the red colors, over the exposed portions of the Bushveld, as well as a pretty big gravity high here, down here. And this is the magnetic data. It's quite magnetic. The upper zone is quite magnetic. So you can also map out the Bushveld, particularly edges with both of these data sets. So very much like Duluth, we use everything we can to show what we know, drilling, locations of xenoliths, seismic data for moho depth. Also here is clear that there are high velocities in the lower crust. So very much the same kind of process that we used in Duluth to get this thickness, average thickness map of the Rustenburg layered sweep. So what you see, this is my part for the northern lobe, and very thick material, 15 to 20 kilometers of very dense material. Tried to make it go away, couldn't. Clearly a feeder, and it's a feeder to the lower zone, and for a lot of reasons, geologic reasons, and geophysically. So we know that it's a big feeder, and it's in the Thabaziming-Murchison lineament, which is where most people, and we would agree, think that most of the magmas came up. It's a major craton boundary, and we see these thick areas in the gravity models that are suggesting feeders within the Thabaziming-Murchison lineament. we see the thickness about 5 or 6 kilometers here, thinning to the edge. And this outline is the outline of where the extent of the northern lobe of the bushveld is. So it extends quite a bit to the west of where it's exposed. Janine Cole also, she did a model for the main part of the bushveld, overlapping with my model. And there are a lot of assumptions in these models about densities, but in particular, things like moho thickness, this lower crustal high velocity, high density layers are poorly constrained, and varying the thickness of those changes the thickness of any Duluth complex, any of the shallower bodies. So I think that the variations in thickness that you see, like thick versus thin, are probably reasonable, but the actual thicknesses take with a big grain of salt. That said, Janine did a very different approach in modeling, and we came up with pretty similar patterns. She sees these thick Mokopane feeder thicknesses along the Thabazimbi-Murchison lineament here, thicker here, thinner here. We have about 1 kilometer or 2 difference in the thicknesses here, which is amazing considering how skeptical I am about how well we can constrain these thicknesses. Janine's model shows south of the Thabazimbi-Murchison lineament, the average thickness of the bushveld is between 5 and 7 kilometers, and it's very thin to maybe non-existent in some of these places. So quite variable thickness. I'm going to talk more about this part of the modeling in Janine's talk, but just to say I did a very regional inversion, very coarse, very simple, the bushveld complex, and come up with pretty much the same patterns. So it's somewhat reliable, the modeling. And I'm going to talk much more about what this means in terms of the lower crust in Janine's talk. Moving on to the Stillwater complex. This is the gravity model. The outline of the complex is here. These squares indicate xenoliths that contain Stillwater complex. This is the magnetic data. High values in red here over serpentinized peridotites, low values over the banded series because it's reversely magnetized. It's also not that magnetic. Once again, same kind of thing you saw for the Duluth complex. We have these various surfaces. This is a Precambrian basement surface from drilling information that we put as starting models. Lower crustallator, this is even less constrained than the other models. Densities from rock properties to try to match this gravity anomaly. These are the results. These show the densities in the mantle and the lower crust that were important to put in this model, and they look a lot like the seismic high velocity regions, but I'm questioning some of this. I still think it should be higher velocity under here. More recently, this paper was done in 2020, and I'm changing my mind a little bit. But the results of the model are this kind of thick area. This is thickness and this is density. So the thickest and highest density regions are here, but there's a little fishtail here. I was trying to decide, well, how much of this might be the Stillwater complex? And that's where magnetic modeling comes in. We know from borehole data and exposure that these anomalies are related, these highs related to the basement to the Stillwater. So if the Stillwater comes in, it's going to disrupt these. So it's unlikely the Stillwater is anywhere over here. So based on the thicknesses and the mag data, we drew this magenta line here as the maximum extent of the Stillwater complex. These are seismic lines that cross it. But I was a little worried. It's bisected by these major faults that may have been faults that localized the intrusion and then disrupted it. So it's quite dismembered. So I put this blue line here, the cyan line, as a minimum extent of the Stillwater. So we have some ideas about the extent. How could this possibly relate to platinum exploration? Well, most exploration doesn't occur deeper than 2,000 meters or at temperatures above 70 degrees. So Heather Parks, one of my co-authors, constructed this temperature map from boreholes, and we put the outline of the Stillwater on them and said, okay, where are the areas that are less than 2,000 meters? There's a little bit of wiggle room because we think we see sediments in the Precambrian basement that was mapped as crystalline basement. And where is it less than 70 degrees? And so what you see is this relatively small area. It still extends past the exposed portion of the still water might be places that you might want to explore, even though these xenoliths out here contain chromatite. So just an example of how we've applied these to something relevant to platinum. Now I'm going to compare our data and to just some gravity models from other intrusions. This is the Great Dike. It's not a dike, it's a layered mafic intrusion. There are tons of dikes that are parallel. It was a big crack in the ground. And there's gravity highs along it, not continuous, and magnetic highs. And there's gravity models across it from south to north. And what we see, this pattern up here are the gabbros, and this white here are they're saying they're dunites, ultramafic rocks. And you see quite a bit of difference in thickness. There's a couple kilometers here, 3 kilometers here. As we move to the north, the gabbros disappear, very thin ultramafic rocks. Here, very thick, 10 kilometers, probably a feeder. And you can see this map shows increasing thickness to the north. So it looks, there's a lot of similarities to the other ones in terms of feeders, but it's a much narrower ultramafic rock because it's just a crack. There's no sedimentary basin for the lavas to go in, which I'll talk about later. This is Skaregard. This is a geologic map of Skaregard. There were modeling done a long time ago, and I did a very quick and dirty model to try to match what other people had done. And using the topography, made a much more simple map. Don't know anything about the lower crust. Here's the gravity, modeled thickness and densities. So we see it's kind of in most of the higher densities. That's the thicknesses are, this is about 9 kilometers. This is about 4, are in a kind of a north-south area, suggesting a crack and perhaps a feeder for part of it. Silen's really interesting because it was placed at 20 to 30 kilometers. It was placed in the lower crust. Remember, we saw those high velocities in the lower crust. This is the kind of thing that could be there. Gravity models show it to be 2 to 4 kilometers with some roots that are 9 kilometers. So this was at the bottom, placed at the bottom of the crust, sliced up during the Caledonine orogeny and placed in Norway. So it lost its top. We don't know what happened to the bottom, so I can't say anything about the lower crust. But the interpretation is this is a layered intrusion, and there could have been other ones on the top. So this could be also acting as feeders to those shallower ones, but that's speculation. Last one I'm going to show you is a very old one from Western Australia. This is gravity highs associated with Windamora intrusion. Similar kinds of things, fairly thick. They didn't say anything about the lower crust, so it's possible that if you've got high densities there, this could be thinner, but I don't know about that. But in any case, part of it's 11 kilometers thick, kind of similar shapes to what we've seen where there's feeders in the Bushveld and the Duluth complex. So how do these things get placed? I mean, we were wondering, what's the role of the sedimentary basin? Do you need faults? And so on. So in the case, this is the Bushveld again. The idea was that it was in place in the Transvaal Basin, certainly this part of it. And now we see this white line is from this gravity model showing where the Bushveld is. And clearly in the Transvaal Basin, most of the thickness, sure, it laps over onto the Archean, but a lot of it was localized by the Transvaal. There are sills of Bushveld out here. I was just in Botswana a couple of weeks ago and saw them, not very voluminous. This is showing MT data from Dana's work in Duluth complex. These colors are indicating very low resistivities, which are associated with sedimentary basin. We don't completely understand this. This is showing her gravity model, thick feeders. This could be part of the feeder. It could be part of the volcanics. Also, the basement can be resistive, but in any case, there's a sedimentary basin there. If you look at a cross section at about 9 kilometers depth, you see these low resistivities, suggesting that there's a basin underneath the Duluth complex. And there are lots of faults that predate the Duluth complex that can continue here. So once again, like the Bushveld, you might have a sedimentary basin, some faults, and here are the feeders. So it might have facilitated the intrusion of the Duluth complex. This is a picture from a geologist showing the emplacement of the Bushveld here in blue into the gap between the sedimentary basin and the older volcanics. Similarly, the Stillwater complex, I mean, the basement is much older, so it's not really a sedimentary basin, but it certainly has, if you look at pictures of it, a lot of discontinuities into which things like, in this case, is the peridotite zone and placed other parts of the system. This is from Corey Wall's picture into the basin. This is interpretation of 3D seismic data from East Greenland. And the reason I'm showing this, and there's a lot of, I went in the literature and it turns out with all of this great C3D seismic data, there's a wealth of information about sills in sedimentary basins. So I use the seismic data to come up with this model. So you've got magmatic underplating. This is lower crust, diking, because it's crystalline crust, which is where the magmatism is likely to propagate as dikes. And intruding as sills, and how they intrude and their shapes depends on the competency of the sedimentary rocks. But as soon as you get out of the sediments, there's not very many sills. Sometimes they follow faults. So this is a way how you can get sills into sedimentary basins, and they extend quite far. This shows numerical modeling of how you can make sort of an intrusion. You have a dike, it hits a discontinuity. And of course, there's lots of them in sedimentary basins, which is why we see, I think, these intrusions in them. And then they can pile on each other as magmatism comes. And, they dome the surface, they make room in a variety of ways. But one of the key things is at the end, Sue's keeping track, because I'm going to go over a little bit, is there's a lot of stresses at the end of these sills and allows them to propagate. And this picture here is actually observational data of mafic sills, lengths versus thickness. And you can get sills propagating 100 to 300 kilometers that are 100 to 500 meters thick. So it would be a way for, say, a Bushveld to get a sill in and get continuity of layering over a long distance with a sill. So this table kind of summarizes what I've been talking about for some of these intrusions. The areas I have here, of course, the Bushveld is a monster, are from our modeling. So they're going to be bigger than what everybody else shows. This shows average thicknesses. They're quite variable, but most of them are less than 10 kilometers unless there's a feeder. These are total volumes from our model. Once again, the Bushveld dominates, Skaregard's little. These numbers I don't believe, but I wanted to put them in here because they're showing the volumes that we have directly below these three intrusions in the lower crust. And in the next talk, you'll see there's a lot more, but my point is there's a lot of magma. So for those people who were talking yesterday about needing 8 to 15 meters of magma for every meter of chromite, no problem. There's tons of it in the system. Not necessarily in the intrusion. Do we see feeders in a lot of them? Sedimentary basins, not always, but mostly. And are there pre-existing faults that help localize the intrusions? Mostly, yes. So this is just what I just said. So I'll finish with my talk now.
Take some questions on.
I can take questions now, or Janine's talk follows directly on this, and so I can do questions later.
Let's go ahead.
For the slide. In your very first slide, you've got a boundary between the upper critical zone and the lower critical zone. I want you to just take it down to the base of the the MG2. The base of the MG2 chromate. That's where it should be.
Oh, okay. I'm sure I got that.
Otherwise, it's wrong.
Well, thank you, but I'm sure I got that from a geologist. There's no way I would put that on there.
Okay, another comment.
What technology did you use for the magnetics for the high resolution? The squid technology?
In terms of what?
No, for the magnetics.
The magnetic data?
Yeah.
Is it helicopter?
So for the still water, it's helicopter data. And for the other ones, it's all fixed wing.
But also this new technology on squid, not.
No, it's, you know, even if you use, I mean, I've used mag data from 1965. I mean, the new data is much better, but for these kinds of things, this scale, and plus the data, for example, for still water is not very good. I mean, we haven't outside of the complex.
Thanks. I really like your comments about that, a lot of magma, which suppose, could you please specify what you're talking about this, where this, are you seeing it in staging chambers or you, or there's a little bit more?
I couldn't have planted you better for the next talk. Thank you, Rice, for introducing Janine's talk.
Okay, do we want to stop it there? We can ask some more questions after the second talk. Janine Cole, who unfortunately couldn't be here,